Okay, we're going to start solving inequalities. We'll start with polynomial inequalities, and we're going to use what's called a test point method. So the general idea is we're going to find the critical points of the polynomial and then use test points to figure out which intervals on the number line make the inequality true. In other words, what the solution to the inequality is. So let's just do examples. I mean, the idea is pretty straightforward as long as you know how to solve polynomial equations. So we're talking factoring, square roots, quadratic formula, etc. So let's jump right into a simple example that we want to solve. And let's say it's x plus 6 times x minus 5 is greater than 0. And what we want to do here is recognize some really nice features. So we really like 0 on the right side, just like when we're solving polynomial equations, we like a 0 here. So that's good news for us. We like that. The other side is factored. That's also really good news for us. What that's going to do is make it easy to identify not solutions like when you solve an equation, but what we call critical values. So the critical values here, well, let's do this first. If I look at the corresponding equation, meaning, what if this greater than was an equals, then it would be x plus 6 times x minus 5 equals 0. And we don't want the x values that make this equal to 0. We want the x values that make it greater than 0. However, the solutions here are really important to us because they're the critical values of this inequality. So the critical values here come from the corresponding equation. They are, well, x plus 6, if that is 0, x equals negative 6. And if x minus 5 is equal to 0, we get positive 5. So those are the critical values. And what we're going to do with those is put them on a number line. And we need to find the numbers on the number line, the x values on this number line that make this inequality true. And so what I'm going to do here is for various x values on my number line, I'm going to map out what happens to the left-hand side. And what I mean by the left-hand side is the left-hand side of my inequality when it's in this nice factored form. Okay, so that's what I mean by the left-hand side. And I want the left-hand side to be greater than 0. So that's what I'm going to keep track of. So let's get started. So let's cut our number line at the critical values, negative 6 and 5. Make sure to do these in the right order. Negative 6 is to the left of 5. And we know that if x is negative 6, if I plug that into the left-hand side is 0. So I'm going to put 0 here. And if I plug in 5 for x, the left-hand side is also 0. Okay. Now what I need to do is I need to look at values in between the critical points. I can pick any values I want. For example, between negative 6 and 5, my test point that I would like to choose is 0, because 0 is between negative 6 and 5. And then what I'm going to recommend, and this will be a theme as you watch me solve inequalities of different types with test points, when you look at the ends of the number line, I always recommend choosing extreme values. And that's because later, when you get to graphing, there's something called end behavior, and these extreme values on the ends are important. So if I want to pick a number to the right of 5, I could certainly pick 6 or 7, but I'm going to pick maybe 1,000 or 10,000 or something really big. And over here, similarly, I'll pick like negative 1,000, okay? Now, what we want to do is plug these x values into the left-hand side. So if x is negative 1,000, you can do this pretty simply without worrying about the actual numbers. Negative 1,000 plus 6 is a negative number. Negative 1,000 minus 5 is a negative number. So a negative number times a negative number is a positive number, okay? If you plug in 0 for x, you get a positive number times a negative number, which is, of course, a negative number. So the left-hand side is positive to the left of the critical value negative 6. The left-hand side is equal to 0 at negative 6. the left-hand side is negative between -6 and 5. The left-hand side is 0 when x equals 5. And finally, when x equals 1,000, 1,000 plus 6 is positive, 1,000 minus 5 is positive. So we get a positive times a positive, which is a positive. So the left-hand side is positive in this interval. Now what we're trying to do, by the way, let me show you a quick trick on my two of my favorite scientific calculators for calculating these values here, the plus, the minus, the plus, which can be useful whenever the left-hand side gets pretty complex. Okay, so let's say we want to plug -1,000 into the expression on the left-hand side. I've got two different calculators here that are two of my favorites that are pretty cheap. I really like the TI-36X Pro a little bit better than the Casio FX115 ES Plus, but they're both really great, and I'll show you how to do this. So first thing we want to do is store -1,000 in for our variable. So I'll type -1,000, and on the TI, my store button's down here in the bottom left. So I'll hit store. And then my variable button here has X, Y, Z, T, A, B, C, D on it. If I want to store it as X, I hit the button one time. If I wanted Y, I'd hit it one more time, etc. So this says -1,000 is going to be stored as X, hit enter, and now it's stored. Now what I want to do is type the expression X plus 6 times X minus 5. So I'll hit parentheses, my X button, plus 6, close parentheses, open parentheses, x minus 5, close parentheses, and it's going to calculate the value of that expression with -1,000 stored for x. And we can see we get a really big positive number. So let me show you how to do the same thing on the Casio. It's very similar. I want to store -1,000. Make sure you use the negative button, not the minus button when you do this. So -1,000 is typed. Now store is in orange here on the RCL button. So I have to hit shift, store, and it's expecting a variable. And on the Casio, the variables, you don't have a button for them. They're in red above other buttons. So here's the X button. Since it's red, you would typically hit alpha first, but since it's in store mode, it's expecting a variable. So I'm just going to hit that button, and I don't have to enter. It's already stored for X. Now I'm just going to start typing over this X plus 6 times X minus 5. Now since it's not in store mode, I'll hit my left parentheses, but I have to hit alpha to access X plus 6, close parentheses, open parentheses, alpha X minus 5, close parentheses, equals, and we get the same value in both cases on the calculators. So now what if you want to store a different value and re-enter it into the same expression? So let's say we want to store 0. So 0, I'm just typing, just continue to type 0, store X. On the TI, hit enter, and now that's stored for X. And rather than retyping the expression, I can use my up arrow to go find the expression that I typed before, hit enter, and it retypes it for me automatically. Hit enter again, and it will calculate its value, which we can see is -30. Same process on the Casio, hit 0, shift, store, and then just hit the X button. Use your up arrow, and you can go find the expression where it was typed before, hit equals, and it recalculates its value, and you can see you get -30 again. So I kind of like the TI a little bit better because it's got a dedicated variable button, it's got a dedicated store button, and it's got multiple lines that you can see at once as opposed to basically one expression on the Casio. But that's how you store values in a variable and calculate its output for different expressions. Okay, so you can see like when you plug 0 in on the calculator, you actually got -30. We don't really care about the 30 part, we just care about the negative. And when you plugged in -1,000, you got that really big positive number. We just care about the positive. When we get to graphing later, we'll care more about, what those numbers are on the ends or even in the middle if you want. Anyway, so that's how you could use the calculator to do these sorts of problems as well. So now what we want to do is we want to know where the left-hand side is greater than 0. In other words, where the left-hand side is positive. Well, the left-hand side's positive here, and the x values that make that happen are the x values to the left of -6. And the left-hand side's positive here, which are the x values to the right of +5. But at -6, we get a left-hand side of 0, which is not greater than 0. So I'm going to put an open circle around that. And the same with 5, because those don't make this true. So what I've shaded here is our solution in what we call interval notation. So the interval notation, because we've got two different regions, I've got to go from -infinity to -6. Here, I go from left to right. So I write -infinity, comma, -6. And for this interval, I write 5, comma, infinity, oops, from 5 to positive infinity. And now we have to talk about the endpoints. Are they shaded or not? Well, -6 is not part of our answer. So with that open circle, that means we put a parenthesis around it. Same thing with 5. It's not part of our answer, so I wrap it with a parenthesis. Now, infinities, no matter how far we shade, we'll never reach them. So they're not included in our answer either. So infinities always get parentheses. And since we've got two different regions, we say x can be in this interval or x could be in this interval. So that or word translates to what we call a union. So it's a capital U. So the way we write our solution here in interval notation is -infinity to -6, not including either one, union 5 to infinity, not including either one. And you can test this. If you plug in a number from either of these intervals, you'll see that this is true. And if you plug in a number not in either of those intervals, somewhere in between, you won't get a true statement. Okay, so you've got the idea now. Let's try some others. Let's try x cubed is less than or equal to 7x squared. Now, in this case, the problem is we don't have 0 on one side. So let's subtract the 7x squared, because we want to use the number line chart to kind of keep track of positive and negative. That's why we need 0, because 0 is between the positives and the negatives. Now, the other side, we need the critical values. To find the critical values, we should factor it if we can. So factoring this, I can pull an x squared out, leaving behind an x minus 7. So this guy right here is going to be our left-hand side we'll use on our number line chart. And we can see that the critical values, if we look at the equation, the values that make x squared times x minus 7 equals 0, well, x could be 0 or positive 7. So let's lay out our number line and sort of track what happens with this left-hand side. So our x values go down here, our left-hand side values go up here, and cut my number line at the critical values 0 and 7. Well, we already know if we plug 0 into the left-hand side, we get 0. If we plug 7 into the left-hand side, it becomes 0 as well. And now, if we plug in test points, let's say -1,000 on the left, positive 1,000 on the right, maybe something simple like 1 in the middle. Well, if we plug in -1,000 for this x and then square it, we get a positive number. -1,000 minus 7 is a negative number. Positive times a negative is negative. If we plug in 1 squared is positive, 1 minus 7 is negative, so we get positive times negative, which is negative. And if we plug in 1,000, 1,000 squared is positive, 1,000 minus 7 is positive, and a positive times a positive is positive. Try the calculator trick here, by the way, too. See if you can become proficient in that. All right, so we have a complete number line chart. We're looking for where the left-hand side is less than 0, which is negative, or equal to 0. So the left-hand side is negative here. It's equal to 0 at 0. So now I'm going to shade that endpoint. It's negative or less than 0 in this interval. It's equal to 0 here. So I'm going to shade that, and then positive from there on. I don't want to include those. So now you can see we just have one big shaded region from -infinity all the way to 7 with no breaks. So we put -infinity, comma 7. -infinity is never included, but 7 is shaded as part of our solution set now. So we use a bracket to indicate that. All right. And there is the solution set for this inequality. Any x value in this interval makes this inequality true, and anything outside does not make it true. Let's do one more, and maybe we'll do two more. Solve. Let's look at, how about x times x minus 4 squared times 3x plus 5 squared. And let's look at where that is less than or equal to 0. Well, good news again is the right side's 0 and the left side's factored. So we can go right to the critical values and draw our number line. The critical values again make the equation true. So x could be 0, 4, or negative 5/3 if you solve each of those factors. So negative 5/3 is first, then 0 is next, and then 4 is after that. And all three of those make the left-hand side 0. Let's pick our test points, negative 1,000, maybe negative 1, maybe positive 1, and positive 1,000. And if we plug negative 1,000 in for x to the left-hand side, we get a negative for x. Negative 1,000 minus 4 is negative squared, though is positive. And similarly, if I square something, I'm going to get a positive there as well. So negative times a positive is a negative. If I plug in negative 1, I get negative for x. Negative 1 minus, well, if I square that, it's positive. And if I square the last one, it's positive no matter what. So we have a negative again. Let's plug in 1. If I plug in 1 for x, that's a positive. And then my two squares are still positives. So I get a positive. If I plug in 1,000 for x, x is positive. Then my two squares are positive. So I get a positive. We have a complete number line chart. We just need to figure out where the left-hand side is less than 0 or equal to. So, all the negatives and zeros are going to be shaded. So here to 0, include 0. Here's negative, include where it's equal to 0. This positive is not included. That's not less than or equal to 0, but this is 0, so I include 4. And there we go. So this is kind of unique. We have two separate pieces here in our solution. The first interval is negative infinity to 0, including 0. And it could be from this interval, or it could be 4. Now, the typical way you'd write that is you'd put a 4 inside a brace. When you have individual numbers, you usually put them inside braces like this, these curly braces. But something I've seen more recently, like using online homework systems, is let me write my infinity better there. How many of you go to write infinities and still write 8s? It took me a long time to overcome that. All right, negative infinity to 0 union, and they'll actually write this like an interval from 4 to 4 and put brackets on both ends. So I've never seen that before, but until recently I've seen it on online homework systems. So sometimes you may have to type it like this. Anyway, so there are two different ways you could write the interval notation for this guy. Okay, let's do one more example. Let's try, how about x squared is greater than 5. So let's get 0 on one side. X squared minus 5 is greater than 0. And unfortunately, we can't factor this. It's not a difference of square. So this x squared minus 5 is going to be our left-hand side. And to find the critical values, I have to solve the corresponding equation, x squared minus 5 equals 0. And it's not too hard to solve. I can just get x by itself. So that means x squared equals positive 5. And then taking the square root of both sides, I get x equals plus or minus the square root of 5. So now those are my critical values I can put on my number line chart. So x, the negative square root of 5 is first. the positive square root of 5 is second, and I know that both of those make the left-hand side equal to 0. They resulted from solving that equation, so you can say the left-hand side is 0. Let's plug in negative 1,000, let's plug in 0, and let's plug in positive 1,000. Let's do 0 first. If I plug 0 into the left-hand side, 0 squared is 0, minus 5 is negative. So notice this isn't factored, so I'm not multiplying to find my sign anymore. So the calculator may be handy here if you want to try plugging in 1,000 for x and then typing x squared minus 5. Let me see. You don't have to do that. I'll show you. I mean, it's pretty obvious you don't need to do that, but if you do, you'll get 999,995, which is certainly positive. But you can see that if you square 1,000 and only subtract 5, you're going to get a positive number. If you square negative 1,000 and subtract 5, you get the same positive number that you do as if you square positive 1,000. So we have our number line chart, and the intervals that we want to look at are the ones that make the left-hand side positive or greater than 0. So everything here, but not including the endpoint, and everything over here, but not including the endpoint, because we don't want it to be equal to 0, just positive. So our solution set is negative infinity to negative square root of 5, not including either one, union square root of 5 to infinity, not including either endpoint. And that's how simple it is to solve polynomial inequalities. As long as you can solve polynomial equations, then you can just use test points to help you figure out which intervals on the number line make the inequality true.